our section 3 of chapter 5, it deals with solving trigonometric functions. So we're always trying to solve it for x. So the first thing that we want to always try to do is isolate our trig function itself. So we know how algebra works. We know all of the how to solve equations. So the first thing that we have to do on this one is add 1 to both sides. Divide by 2. Okay, now essentially what we're doing is finding the inverse sine of 1/2. I think the easier way to figure that out, or to think about that, is to look on our unit circle, and we want to know where sine of x, which is the y value, is equal to 1/2. So that occurs on the unit circle at pi over 6 and 5 pi over 6. Okay, so we would list those two. Those are the only places that our y value is 1/2. And because trig functions are periodic and repeat, what we're going to do is add to the end of our answer here, add 2n pi, where n is any integer, because it would repeat itself 2 pi after pi over 6, another 2 pi after pi over 6, and it would also go backwards if n was negative. So for solving trig equations in general, we always have to have the plus 2n pi on the end. Okay, so pretty straightforward. We're just trying to always get those sine functions by themselves. So on this equation, on this question, we have sines on both sides. So I'm going to actually just add this sine over to the left side with this sine. So we have 2 sine x plus the square root of 2 equals 0. And again, we're trying to solve for sine x. So subtract the square root of 2 and divide by 2. Now in this example, it's a little bit different because it just says between 0 and 2 pi, which means that we're not taking into account the fact that sine is periodic. We're just saying, okay, on the unit circle, where is sine of x equal to negative square root of 2 over 2, which happens at 5 pi over 4 and 7 pi over 4. So when it tells us that we're in the interval, we do not have to add the plus 2n pi on the end. Okay, so this is a tangent, so we have to isolate tangent instead of sine, but it's always the same, just isolate the trig function, add 1 to both sides, divide by 3, take the square root. Now when you take the square root, you have to remember that it's plus or minus, so we're going to have more answers. So plus or minus 1 over the square root of 3. And tangent's a little bit harder to find just because it's y over x. So you don't just look at it and say, okay, there's the y value. You actually have to do a little bit more work and divide the y over x on the unit circle. So we're trying to find where we get 1 over the square root of 3, either positive or negative on the unit circle, which happens at pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6. Now, tangent is also periodic, but it doesn't have a period of 2 pi like the sine and cosine functions do. So we're just adding n pi onto this. And this is a little bit tricky at this point because there are 4 values on the unit circle that we found, all 4 that I listed here. And then when we add the n pi onto it. But if I'm just looking at the first 2 answers, if I was to add n pi onto those 2, I actually get my other 2 answers. So I don't even need to list these. They're included in the n pi. So I just have to say pi over 6, 5 pi over 6, plus n pi. I don't have to list all 4 for tangent. Okay. Solve cotangent times cosine squared equals 2 cotangent. So I need to get everything on the same side first before I can do anything. And then just like if I was doing this with variables instead of trig functions, I want to factor out anything that's similar in those 2 terms. These both have a cotangent in common, so I factor that out. So as soon as I turn it into multiplication, then I can really just split this up and have two different problems. So I'm going to start on the left side. I need to know where cotangent of x is equal to 0. Remember, cotangent is x over y. So where, on the unit circle, if I did x divided by y, would I get 0? That happens at pi over 2 and 3 pi over 2. But remembering that cotangent also has a period of n pi, I only need to list the first one as long as I say plus n pi. And I have to say plus n pi because it doesn't just say in the interval from 0 to 2 pi, so I know I have to include all of the periods of cotangent. Okay, so now we're going to solve the cosine. Alright, so I have plus or minus the square root of 2 for cosine. So that doesn't ever happen on the unit circle, but that doesn't mean that it doesn't exist. It could just not be one of the angles that we're familiar with. So what you want to do then, if it's not on the unit circle, is just take the inverse, inverse cosine of either plus or minus the square root of 2. And when you do that on a calculator in radian mode, you should get, it'll tell you domain error or that it's upset with you. That means that that doesn't exist. So the only answers to this would be our left side, the pi over 2 plus n pi. Find all solutions of 2 sine squared minus sine minus 1 in the interval. So I have three terms, a sine squared, a sine, and a constant, which means we should factor this. Since it's a trinomial, it gets factored into two binomials. And factoring this, I get 2 sine x plus 1 and sine x minus 1. And just like the last one, now that we got it down to multiplication, I can split this into 2 and solve them separately. Starting on the left side, negative 1/2, which occurs at 7 pi over 6 and 11 pi over 6. And then where sine is equal to 1, that happens at pi over 2. So all three of these x values, that is my answer. So I have another trinomial, but I'm noticing that my sine squared and cosine, those are two different variables essentially. So I need to turn that sine squared into cosines. Sine squared is 1 minus cosine squared. So now once I distribute and rearrange, I'll have everything in terms of the same variable, and I can factor this. I'm also going to, once I move the 2 over, so that'll be negative 1, I'm also going to multiply everything by negative 1 because I don't want a negative 2 in my front. So I'm going to multiply by negative 1, 2 cosine squared minus 3 cosine. That would be plus 1. Okay, so again, that was putting the 2 in with the negative 3, which would be negative 1, and then I multiplied everything by negative 1. Now I factor. Once I factor, I turn them into two separate problems. And I get where cosine is 1/2 pi over 3, 5 pi over 3, and cosine is 1 at 0. So I list all three answers because it does not say that I'm in the interval from 0 to 2 pi, meaning I have to add the n pi, 2 n pi on the end. So 0, pi over 3, 5 pi over 3 plus 2n pi. And that's how I would write my answer. Okay, so squaring. So this one, I have cosine x plus 1 equals sine. Solve it for x in the interval from 0 to 2 pi. I can do absolutely nothing with this. Even if I subtracted the sine over, this is actually completely useless. But what I can do is square both sides, since I'm doing it to both sides. That's all right. Okay. And then I need to get everything in terms of the same variable, so I can convert sine into 1 minus cosine squared and move everything over to the left side. And factor out 2 cosine. Now that I turned it into multiplication, I can turn it into 2 separate problems. All right, so I get pi over 2, 3 pi over 2, and pi. And the extra step here, since I had to square both sides, okay, this is a special kind of problem. When I have to square both sides like that, I need to test all 3 of my answers in original to ensure that they all work. When I do that, 3 pi over 2 does not work. So my answers are just pi over 2 and pi. Okay, so you have to test your answers in the original when you square both sides like that. All right, so this one looks a little bit different because there's a 3 in our cosine function. I'm going to isolate it the same way. This time when I find my angles on the unit circle that are equal to 1/2, I don't just say t equals 3, whatever the angle is right away. I use 3t equals my angles that I find. I find pi over 3 and 5 pi over 3. So now since it's 3t equals those angles, I need to divide the angles by 3, and then I'll have my actual answers here. And I also have to add the 2n pi, and this part's a little weird. When I add the 2n pi, I also have to divide that by 3. Okay, so when we have a multiple angle other than just t, x, theta, whatever, I need to make sure that I divide everything in my answer by 3 or whatever number's in front. Okay, so now I have 3 tangent of x over 2 plus 3. I'm going to isolate it the same way I always do. I subtract 3 and divide by 3, I get -1. Now I'm looking where tangent is -1 on the unit circle, which happens at 3 pi over 4. And I don't have to list the other one on the unit circle because I always add the n pi, so I only have to include one, and then because of the n pi, the other one gets included. So the 3 pi over 4 is the only one I have to list. Remember, we're adding n pi. And then x over 2, I need to multiply everything by 2. So my actual answer then is 3 pi over 2 plus 2n pi. And our last question. I need to turn these into the same variable. Secant squared needs to be turned into 1 plus tangent squared. It's a Pythagorean identity. Subtract over the 4. And factor. I can turn it into two separate problems. I'll start with the right side because we know where tangent of x equals -1. This happens at 3 pi over 4. And the inverse tangent of 3, so the tangent is not equal to 3 anywhere on the unit circle, but if I take the inverse tangent of 3, I do get answers on my calculator, which means that it does work. It's just not on one of those nice angles on our unit circle. So I would just say inverse tangent of 3 here to avoid icky decimals. So I have the inverse tangent of 3 and 3 pi over 4, adding the n pi. Okay, and that is our section 3 on solving trig functions.